Hey guys, my name is Eli Park, and I will be going over CNCM Online Round 3 Problem 3, which is written by me. So let's read the problem statement first. Let a of 1 equal to 1 and a of n plus 1 equal a of n times p of n for n greater than or equal to 1, where p of n is the nth prime number, starting with p of 1 equal to 2. Let tau of x be equal to the number of divisors of x, and find the remainder of this summation when it is divided by 91 for positive integers d. Okay, recall that the d bar a of n denotes that d divides a of n. So we'll be dividing this problem into two parts. The first part, which is the more important part here, is going to be evaluating the inner summation. So we're going to be trying to find a closed form for this for some with only a variable of n remaining. So then the second part was going to be extracting the answer. It seems like we're going to have some large number, which is the reason why the mod 91 is asked for. So let's get going right away. So what we want to realize first is that how A is defined, it's defined such that it's the product of several different primes. So in its prime factorizations, you're not going to see an exponent of 2. That's what's important here. That what makes our tau function summation going to be easier to evaluate. So if I may, so what we're going to be doing is that first, we're going to be classifying all possible d that divides a of n into n different groups. And how the groups are labeled are by the number of prime factors that they have. So we'll have a group group 0, a group 1, a group 2, a group 3, all the way to a group n minus 1, okay? So what we want to do for each group is evaluate tau of d so we can sum them all together. So for first step to evaluating the sum of tau of d in each group is to first realize how many of our numbers are in each group. Well, in the 0 group is actually fairly obvious. There's only one number. That number is 1 because no other number has no prime factors. So that's fairly easy. Then we move on. So into group 1. How many numbers have only one prime factor? Well, amongst the numbers d that divide a of n, there has to be exactly n minus 1, right? Because a of n is actually just the product of n minus 1 primes. So there's n minus 1 possible prime factors of a of n, which are the things that go into this group 1. So we keep going into group 2, and we try to find how many elements are in group 2. Well, remember what the group 2 means. Group 2 means that we're trying to find the factors of a of n that have exactly 2 prime factors. Well, what we can do is that we can actually just select 2 of the prime numbers from this list of n minus 1 primes, and if we just multiply them together, that's what we're going to get. So if you think about it, we're choosing 2 prime numbers from a group of n minus 1 distinct primes. That's actually just going to be n minus 1 choose 2. That's interesting. And then if we keep going, we're going to realize that this is going to be the case here for the group 3. We're going to have n minus 1 choose 3. And going all the way to the end, we get that this should be by our pattern n minus 1 choose n minus 1. And this is verified because the only factor of a of n that has n minus 1 prime factors is going to be a of n itself, which is just equal to 1. So, and then this is also verifying our previous two results at group, this is verifying our previous two results at group 1 and group group 0 and group 1, where we can replace this with n minus 1 choose 0 and n minus 1 choose 1. So now that we've evaluated the number of elements in each group, now we can try to find tau of d for each group? Well, and this is, we'll see here why we strategically divided up the groups like this, because tau of d is the same in each group. Tau of d for group 0 is just going to be 1, because the only element is in that group is 1, and 1 has exactly 1 divisor itself. So that should make sense. And then for group 1, we're going to have 2, because each number in that group is actually just a single prime, and each prime has 2 divisors, 1 in itself. So we're going to have 2. So we don't see the pattern yet, but now we should, from this group, we're going to start making sense. So let's consider, so we want to find tau of group 2. So let's consider the number 6, which is just P1 times P2, okay? Or equal to 2 times 3. How many divisors does this have? Well, it has 1, 2, 3, 6, equal to 4. That should make sense. And then if you can classify this into P1 and P2, you can generalize this to 1, P1, P2, and P1, P2. So there are 4 divisors, and we can write that down. But before we start jumping onto our next group, we have to realize what is going on here. First want to notice the pattern. We see that we have in these groups a 1, a 2, and then a 4. This is suggesting powers of 2, but we first want to make sure that this is true before we move on. So let's look at group 3 next, just to ensure our pattern. Well, let's say we have a number like 2 times 3 times 5, which is 30. You could actually try listing out all the factors, and you'll get exactly 8, which follows our powers of 2 pattern, but there's a better way to do this. I like to think about each prime number as a little light switch. So let's say, and then each light switch is on or off. So let's say the 2 light switches on, which is marked by a 1, and then 3 light switches off, and then 5 light switches on, okay? So this denotes 2 times 5 is equal to 10, which is a factor of 30. You'll see that each combination of light switch is going to lead to a factor of 30 because we're just multiplying together its prime factors one at a time. So, and then we can also see that this covers all the factors of 30 because 30 has no exponents in its prime factorization. Well, exponents greater than 1. So you can think about each of these as a light switch, and you can run through all the combinations of the light switch: 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1, and realize that this is just 8, and this should be pretty obvious. This is actually equal to 2 to the third to be exact, because there's 3 light switch, and there's 2 ways to turn on each light switch. And then, yeah, this doesn't necessarily make sense. I can write out what each of these would be, and hopefully this should make sense here. So we have 2, 3, 5, and then 1. So we have that for each we see that these are going to be the factors of 30, and then we will continue, and then this becomes 2 to the third power, and then we can actually continue for each group here, and then this final group is going to be multiplied by 2 to the power of n minus 1. So now we have this nice looking summation that we could, I'll make the lines a little shorter. So now we want to sum this all together and see what you get, okay? So to precisely, I could write it out like this. I could write it out for, oh, sorry, that was bad. For, this is not going to erase. So for sum k equals 0 to n minus 1, we're summing 2 to the k times n minus 1 choose k. And this should be familiar. This is actually just the binomial expansion. And by the and this is actually, just to be specific, this is a binomial expansion of 1 plus 2 to the power of n minus 1. If you're not very familiar with this, you should try looking it up, and I encourage you to think through this. This is 1 plus 2 to the power of n minus 1, which is equal to 3 to the power of n minus 1. So actually, what we've just did now is that we found a closed form for that portion, and that's equal to 3 to the n minus 1. So what remains for us is to evaluate the sum of from n equals 1 to 20 of 3 to the n minus 1, all divided by 91, or taken mod 91. So what this is, though, is that this is actually just a finite geometric series. Expressing this as a difference of two geometric series, we can get 3 to the 2019 over 1 minus 1/3 subtracted by 3 to the negative 1 power divided by 1 minus 1/3. And then this, if I may, I will use the next slide to express that out. This will be 3 to the 2020 minus 1 over 2. We get this by just putting these two fractions together on a common denominator and multiplying by 3 on the top and bottom. So now we just need to take this mod 91. So what we could do is that we could first take 3 to the 2020 minus 1 minus 91, and then divide that by 2. Using the Euler-Tauschen formula, we can take the exponent of 3, which is 2020, mod phi of 91. Phi of 91 is equal to 6 times 12, which is 72. So we can just replace this exponent 2020 with its mod 72. And evaluating 2020 mod 72 is going to give us 3 to the 4 minus 1 mod 91, which gives us 80 mod 91. So that means that this is equal to 80. But we want to find this. So we have to make sure to include this division by 2. So including the division by 2 yields us an answer of 80 divided by 2, which is equal to our ultimate answer of 430. Thank you for watching this video.